Now our topic is generalizability and applications of results of empirical research. Let's first talk again about the differences between internal and external validity. So you remember that internal validity of a study really refers to its integrity or the logic of its design and the extent to which a study adequately answers its central questions or tests its hypotheses. For experiments, internal validity is the extent to which the study provides unbiased tests of causal hypotheses and eliminates confounding factors or other explanations. External validity, our topic for now, is really synonymous with generalizability. And this is the extent to which research results can be applied to other samples, settings, and times. For purposes of internal validity, we often use random assignment to treatment and control groups to minimize threats to internal validity. For purposes of external validity, we use random selection of participants from a population to minimize threats to external validity. But don't confuse these random things. Random assignment and random selection are very different. They're done for very different reasons. So let's make sure you understand this. Looking at the picture on the left, random assignment, again, minimizes threats to internal validity by starting with a sample and then randomly assigning sample participants to two groups, or maybe three groups, treatment and control groups. Now, the reason we do this is to get groups that will be alike in all aspects except for the kinds of treatment they receive, so that in the end, when we compare these groups on outcomes, any differences between the groups should be due to treatment and not to pre-existing differences. So this helps us establish causality or support causal inferences. Random selection, on the other hand, is done again to minimize threats to external validity. Now we do this by starting with a population, a target population that we want to generalize to, and we draw a sample using probability theory that is representative of that population so that we can use information on that sample to make generalizations about the population. Now, probability samples aim to produce results that are representative of a larger population. We use probability theory to do this, and this allows us to estimate population parameters within certain confidence intervals. Here's a formal definition. A probability sample is a sample that's drawn according to random selection procedures in which every member of the target population has a known non-zero chance of being included in the sample. So you see that every member of the target population has a chance of being included in the sample, not necessarily an equal chance, for reasons we'll talk about in a minute. You can think of this like a lottery in which everyone gets at least one ticket. Every member of the target population gets at least one chance to be included in the sample. Some people get more than one ticket, so the chance is not the same for everybody, but everybody has some chance. Probability samples use a two-step procedure. First, they start with a sampling frame, which is a list of all of the eligible elements in a target population. Here, elements could be individuals, or they could be households, or they could be agencies, but the element is the thing we want to sample, the unit we want to sample. And if a sampling frame includes a list of all of the eligible elements, then we're going to take a sample from that list. So you could think of this like an old-fashioned phone book that has names and addresses and phone numbers of people, but that's not a comprehensive list of all of the residents of a village, let's say, because it doesn't include the people who live there who don't have phones. So you have to think very carefully about whether your sampling frame really includes all of the people in your target population, or whether it systematically excludes some people. Once we have a sampling frame to work with, we're going to use some form of random sampling or probability sampling to select study participants from that list. So here are some types of probability samples. A simple random sample uses random selection from a sampling frame with replacement. This is done to maintain the known chance of selection for each element in the sampling frame. Now, you don't have to worry too much about this issue of replacement, but just understand that in a simple random sample, every element has some chance of being selected, and we're using a variety of procedures, maybe putting all of these slips of paper into a hat and pulling out slips, or using a random numbers table, or using computers to generate selection from a sampling frame. An efficient and some ways more straightforward procedure for doing this is called systematic random sampling. Here we would scramble our sample frame so it's in no particular order, and we would pick a random starting point, and then we would select every so many elements where that selection interval is called the sampling ratio. So we calculate the sampling ratio by figuring out what size of sample we want and how many elements there are in the target population. So for example, if I want a sample of 100 people from a target population of 100,000, I calculate the sampling ratio by dividing 100 by 100,000. So my sampling ratio is 1 in 1,000. So that means I'm going to use my systematic random sampling procedure to pick a random starting point and then select every 1,000th element in the sampling frame. Every 1 in 1,000 elements will be selected for my sample. A stratified random sample first sorts the sample frame by what we call stratifying variables, and then it samples within those strata or subgroups using either systematic or simple random sampling procedures. I'll show you pictures of this in a minute. A fourth type of probability sample is called multi-stage cluster sampling. This is useful when we don't have a complete sampling frame, and I'll give you some examples of that in a minute. So stratified random samples take a population and divide it into strata these are important subgroups for the purpose of this particular study. And then they take random samples of each strata, each subgroup, to make sure that the groups are represented in some way in the sample. So we might be sorting by age or religion or ethnicity, and then taking random samples of each groups to comprise a sample for the study. This is useful when we want to make sure that certain subgroups are adequately represented. And there are two approaches to doing this. We can have proportionate stratified random samples where subgroups are represented in our sample in proportion to the numbers they have in the population. Or we can use disproportionate sampling to oversample certain small subgroups to obtain enough information on those subgroups to use in comparisons with other groups. So here you see on the right there are examples of this. In stratified sampling, again, there's some subgroups in the sampling frame, and we're going to break the sampling frame into these groups and then random sample from each group. In the proportionate sampling example, we sample black X's and red X's. There are more black X's in the population, so we find more of them in the sample than we find red X's. But let's say we really want to compare black and red, and for purposes of our study, we want the sample to be divided between black and red equally for purposes of comparison. If that's the case, we're going to have to oversample one group in order to get equal numbers in the sample. Here's an example of a disproportionate stratified sample. Here we're interested in studying women over the age of 50. And in the population, the squares on the right, you see the proportion of women in this population over 50 who are Hispanic, black, and white. But for sample purposes, we want equal numbers of these women so that we can make comparisons between these three groups. So we're going to disproportionately sample them. So we're going to get 4 Hispanic women, 4 black women, and 4 white women. Cluster samples are used for when we have lists of clusters or groups, for example, lists of schools, but we don't have a sample frame that includes all of the individuals within those clusters. So for example, it's not likely that you could get a sampling frame that includes the names of all children enrolled in elementary schools in Pennsylvania. That list just does not exist for reasons of confidentiality. But you can get a list of the names of the schools, elementary schools, in the state of Pennsylvania. And you could simply sample schools. So let's say we have 9 schools in a county in Pennsylvania, and we want a sample of those schools. We could simply sample 3 and then study those 3 schools as entire entities. Now the picture on the bottom shows a multi-stage cluster sampling scheme. So instead of just taking the whole cluster, we're going to do this in 2 stages. We've selected 3 schools, but we don't want to study the whole schools. We want to study school children, let's say. So we're going to take samples of children within each cluster. So the multi-stage bit means that we've done this in 2 stages. 1, sample clusters, and 2, sample individuals within clusters. Now we have a sample of school children that is representative of all of the children in these 9 schools. And they're representative because we've used random sampling at each step. 1 to select clusters, 2 to select individuals. Now, multi-stage cluster sampling can use 2 or 3 or more stages. So for example, a 2-stage process samples clusters and then samples elements within those clusters. A 3-stage procedure could sample clusters like schools, and then sample clusters within those clusters like classrooms, and then finally sample elements or individuals within those smaller clusters, so sample children or teachers within classrooms. There are an infinite number of ways of doing this. You can set up multi-stage cluster samples in ways that are very refined for the specific purposes of a study. Now, there are also a set of non-probability samples, and we will use non-probability samples when external validity is not as important as other aims of this study. So if we're using non-probability samples, we're very limited in the extent to which we can make generalizations about a larger target population, because we're not using random sampling or probability sampling to create the sample. So we're letting go of all of the assumptions of probability theory. But sometimes there are very good reasons to do this. So if construct validity or internal validity is particularly important to you, you might use a non-probability sample and understand that generalizability is going to be limited. So looking at these types of non-probability samples, a convenience sample is simply a sample of people who are easily available to you, people who are interested in the study or who volunteer. An example is if you're talking to people who are shopping at a mall. It's not a probability sample, doesn't represent any larger target population. It's a sample of people who are easily available to you. Talking with your colleagues at an agency or clients in an agency are other examples of convenient samples. Now, another way to take a non-probability sample is to use a purposive, sometimes called purposive or judgmental sample, where you're choosing participants to participate in a study because they have certain characteristics. So this is, you have explicit reasons for picking people to be in your study. Now, I've done this sometimes in studies of social workers or child welfare caseworkers, where we have picked caseworkers because they are experienced and articulate. They're interesting to talk to, they can teach us a lot. They're not representative of caseworkers per se, Whoops. But we're not trying to create a representative sample. We're trying to learn as much as we can from caseworkers. So we pick this purposive sample of experienced, articulate, thoughtful people. Another way to go about purposive sampling might be to purposefully pick extreme or unusual cases, or to pick very typical cases. They might not be representative of a population, but they're telling you something that you want to know. Another type of probability sample is called quota sampling, and this is essentially a stratified, non-random sample. In quota sampling, we identify the key characteristics for purposes of the study and for sampling, and we create a tabular display with the desired number of participants in each cell. I'll show you an example of this in a minute. But finally, the final type of non-probability sample is called a snowball sample. And this is very much like a multi-stage scheme, where you begin with key informants, people who you'd like to learn from, and you can do this in any way using convenience, purposive, or quota sampling. And then you ask them to identify others, so that's the second stage. You could ask them to identify other people who are like them or people who are not like them, and to give you contact information so you can follow those people in your study. Now, snowball sampling is absolutely the best way to get information from key informants on gray literature for purposes of a systematic review or meta-analysis. Begin with key informants, people who know something about the research in that area, and ask them who else you should talk to. So here's an example of a quota sample. Let's say we're interested in studying social workers in hospital settings, and we think we want a sample size of about 40 people. We first ask ourselves, well, what are the important stratifying variables? What kinds of people do we want to make sure we have represented in our sample? And perhaps we decide that some of the important differences among social workers in hospital settings might be represented by an urban versus other setting split. Urban hospitals are very different in their networks and relations with other agencies than non-urban hospitals, so we'll use that as a stratifying variable. And maybe another important difference for purposes of our study is how much experience the social workers have. So we'll create another stratifying variable that is years of experience, and we'll operationalize that as less than 5 years of experience versus 5 or more years of experience. So now I have a quota sample scheme that shows me that I'm going to try to find 10 people in each of these cells. 10 people in urban hospitals with less than 5 years of experience, 10 people in urban hospitals with more than 5 years of experience, and so on. That's my quota sample scheme. Let's talk about how we can generalize from sample data. Some rules of thumb here. Non-probability samples don't usually provide generalizable results. Probability samples can provide generalizable data, but the results can be biased due to incomplete sampling frames and to what's called non-response bias, which is very much like differential attrition. Let me show you a picture of this now. So here are the kinds of sampling problems we can encounter in probability samples. We start with a target population, but again, if our sampling frame is not complete, we could systematically omit some kinds of people. And then from the sampling frame, we identify a random sample, but that sample could be altered by loss or differential attrition. So people might leave our sample for certain reasons, and that introduces some bias in the final sample. So these are problems that could be encountered in probability samples that would compromise our ability to generalize from sample data to population parameters. Now, external validity also uses this idea of proximal similarity, an idea from social scientist Donald Campbell. And he said that study results are more likely to apply or generalize to situations that are similar to our study than to dissimilar situations. So external validity is not all or nothing. It's not the case that results either apply outside of the study or they don't apply. The question is, how similar are the applications? Results of our study will apply to similar settings, people, places, and times more than they apply to less similar settings, people, places, and times. To think about this more carefully, we have these frameworks for thinking about proximal similarity and generalizability. So here are two frameworks for thinking about the components of proximal similarity. Pick one. You don't need to use both if you're concerned about this. So you could use our PICOS framework. And here the question is, to what extent are the participants in a study similar to populations and problems outside of the study that I want to generalize to? To what extent are the interventions or independent variables or predictors in the study similar to the treatments or variables, predictors that I want to generalize to outside the study? And so on. Again, use either the PICOS or the MUTOS framework. They're very similar. So how do we apply research results in practice? Research results never tell us what to do. That's not what they do. Jack Rothman wrote a wonderful article a long time ago that's called Conversion and Design. He said, with research results, we first need to convert these findings into directions for action, and then we need to design specific action steps to take. So conversion involves formulating this basic plan of action, and design involves the more detailed articulation of implementation plans in a specific application environment. Importantly, Rothman said that this process of conversion and the process of design are not research activities. They require other kinds of information that go beyond empirical data. They require informed choices based on values, preferences, resources, experience, and so forth. So this is a very important activity or set of activities for policy, program development, and practice. So let me give you a conversion and design example. Here's a fairly robust research result. In a series of large statewide randomized controlled trials conducted over many years, my colleagues and I have found repeatedly that intensive in-home services do not prevent the out-of-home placement of abused or neglected children in the U.S. Now, this finding was initially viewed as something of a disappointment because it was hoped that these services would prevent placement. But the results of the research in multiple states show that that is not the case. Now, conversion and design. What do we do about this research finding? Well, we have to convert it into a plan of action. So what should our plan of action be? So here are three alternatives. We could decide, based on this research, that we're going to change the services. We're going to change the way we do this, maybe to try to have a different impact. Or we could change the target population. We could decide to send different kinds of families into these programs, maybe again to try to change the impact. Or we could change the goals of the program. We could say, well, these programs don't prevent placement, but they're doing other useful things in child welfare, so we're going to change the goals and have them aimed at different outcomes. But you can see that whatever your course of action is really driven by values, preferences, and choices among alternatives. We can't do all three of these things at once necessarily. Whatever our course of action is, then drives the next steps. So our design of specific action steps depends greatly on the course of action we've chosen. That's it for now. Talk to you soon.